You gotta be kidding.
No, we're learning.
Quickly review mass versus weight. We talked about that. What's the difference?
Gravity.
Oh, what about it? Gravity's a big part of it.
Gravity can change.
Mass
Depending on where you are.
Weight is determined with gravity.
Okay, weight is the force of gravity, right? That's another way of saying it. So it's the force that's transmitted by two objects' gravitational attraction. Okay, good.
It's mass, like the difficulty of changing the direction of the object.
Okay, so mass, somebody expand on that. Mass is, let me rephrase what you said. The distance, difficulty of changing direction. So it's resistance, an object's resistance to changes in its inertia, right? Okay, what is mass? Thank you. Where does mass, what's it fundamentally about? What causes an object to have mass? Matter. Yeah, it's matter. Right, so at some level, mass is really just it's an accounting of the pile of matter that's embodied in some material. That's gonna look different depending on what element it is and how it's constructed, right? Different materials have different densities, but that's mass. Okay, so what does a scale measure? Weight? Okay, does a scale always measure weight? When would it not? When would a scale not measure weight?
With zero gravity?
What's that?
With zero gravity?
Okay, there wouldn't be any weight in zero
So
gravity.
does it change with, like, if you're pushing it down, you're like changing its length?
Okay. Okay, so let's take a hypothetical example here. So let's say that we're in an elevator and we're standing on a scale. And if a person has a weight of 200 pounds, if there's a weight of 200 pounds and the elevator is stationary, what is the scale read?
200 pounds.
200 pounds. What if, though, the elevator starts to accelerate upwards from rest, for example? Let's say
It would
you know,
increase.
that you're not going to weigh more, but the scale's going to read more, isn't it? Right? Give me an estimate here. I want you to think about this a little bit. If the elevator is accelerating upward with an acceleration of 1 meter per second squared, assuming gravity is about 10, just to make the calculation easy, what would the scale read?
220.
About 220, right? Do you see that? Because that would be a 10% increase in the acceleration that the body's experiencing, right? Does that make sense? And so, yeah, you'd see it would read about 220. What if it was going down at about just a little, well, we don't have to get exact with it, but if it was starting at rest and it started to decelerate, or started to accelerate down, we should say, that's not deceleration. Deceleration is slowing down. If it started to accelerate in the negative direction at 1 meter per second squared, conversely, what would you feel? You'd feel lighter, and the scale would read less, wouldn't it? Okay. So once again, does a scale measure weight? It doesn't. It doesn't really measure weight. It is used to measure weight if the system is at rest or is not experiencing acceleration, right? Then it's useful, but it doesn't really measure weight. What does it measure? Let's look at a picture. If we draw a picture here of just a representative picture of a scale sitting in an elevator, how about, let's say?
Internet's back up, by the way.
Oh, it is back up?
Yeah.
Okay, good. So here's our scale. And here's a person standing, the person, I guess. There's the person standing on the scale. All right, thank you. Not here, here, here. You want to take one and pass it. So what are the forces acting then? Now let's the forces acting are kind of, there's a lot of forces acting here, depending on where you look. But if we're just looking at the system, how about inside the elevator cage? What are the forces acting in? See if we can define all the forces that are acting.
Gravity.
Okay, so there's the weight of the person acting in which direction? Down. Okay, so we could draw that. So we know that there's mg acting down, right? The weight of the person. What else?
The floor pushing back up.
Okay, the floor is pushing up on the scale. Let's just assume that the scale is kind of built into the floor here, right? So then there's the force of the floor, which is the scale, pushing up, right? That's what I'll do with this. So the floor is pushing up, and that's it, right?
Mhm.
And if the two are at rest, then they cancel out. Or I mean, if the elevator cage is at rest or moving at constant velocity, so there's no acceleration, they cancel out. Okay, what are we going to call that force that's pushing up? It's sort of like a buoyant force in a way. It has a name. We call it, and the reason we call it this, I'm going to talk about later. But for now, I'm just going to give it to you. It's called the normal force. I'll tell you how, actually. And a lot of times in our online textbook, they call it that. Yeah. Which I kind of like, but what's the one problem with that? What is it? It looks like a Newton, right? So how do you know when it's a Newton and when it's not? It's context, right? It's context. And then this one, this is a vector also, but a lot of times we don't put the vector hat over it. And I guess we could put the vector hat over the G if we wanted to, right? But we always just assume, because it's an arrow representing a vector, we know it's a vector quantity. What are our options for normal force? There's really no good option here to avoid some confusion. And so if you call it a capital N, it sort of interferes with the concept of a Newton, because a Newton is always written as a capital N. That's our short, our shortcut way of writing Newton. The other ways you could write it, you could say, why does it do this sometimes? I don't get this. Does somebody tell me why this board sometimes lags like it does? I have no idea why it does that.
I thought you had to press the flame.
You can recalibrate.
That's for calibrating. Sometimes it just like the internet goes slow or something with that. It's not really the internet. I don't know what it is. My computer. I don't know if it's like doing some kind of is it kind of a virus search or I don't know what it's doing. What about that one? That's the other way we could say normal force. What's the problem with that one, you suppose?
It's the same as net force.
It looks
Or
like
close.
net force, right? Because a lot of times we'll write net force like that, but they look pretty similar also then, right? So you're kind of stuck here. I mean, so this is what our online book does, so we'll just do that. That's what the Open Standards book does. What's that? Well, it does. It has a vector hat on it.
Like pointing upwards the same.
Well, because it doesn't always have to point upward. It could point in other directions too, right? Because the normal force in this case, it's the contact force between the floor and the person, right? But like if I were throwing a ball, then what's the force acting between my hand and the ball? It's a normal force too, isn't it? Right? It might be acting in that direction.
If you jump up and hit the ceiling, is there a normal force
Yeah.
down on your head?
Yep.
So a
It
normal
would
force
be.
is contact between two objects?
Yep, contact between two objects, right. Okay, so then how could we show here, using a free body diagram, why the scale is going to read more if the elevator is accelerating upward?
Because the normal force is increased.
How are we going to draw that? So free body diagram, we're going to simplify it by just, this represents the person, right? The force is acting on the person. And really the scale is just measuring the normal force acting on the person, right? So I got two forces. I've got the normal force pushing up, and I've got the weight pushing down, so I'll just call it W for weight for now. How's that? And what's the net force there in this case? It's supposed to be
Zero.
supposed to be 0, but if there is a net force, that would account for a net acceleration, right? So if there is some net acceleration upwards, right, I guess I should call that MA for a net force, right? Because that's what Newton's second law tells us. Net force is just equal to mass times acceleration. Then what would I have to do to this free body diagram? That's a bad color, isn't it?
Yeah.
Let me choose a better color. Let's go with this one.
Hurts your eye.
What do I have to do? How long should I make this vector if I want there to be? It's got to be a little shorter, doesn't it? It has to be imbalanced, right? It's got to be imbalanced. The normal force has to exceed the weight if there's going to be a net acceleration upwards, and so therefore the scale is going to reach something artificially high, right? Now, is your weight going to change in the elevator? No, your weight's going to stay the same. So the only thing that's going to change, if we want to have a net downward acceleration, right, like you're starting from rest and it starts to accelerate downwards, you can all imagine what that would feel like, then this is the vector that's going to change, isn't it? Right? So this one would have to shorten up so it was shorter than the weight. Okay? Okay, good. So a little picture here. So here's a little example that kind of represents normal force, and it gives you a little idea about what normal force really is. So before the guy sets the dog chow down on the table, he's providing the lift force, right, that offsets the weight of the dog chow. When he sets it down on the table, he lets go, and now the table supports the weight. Well, how does the table support the weight?
Normal force.
Normal force. Now, what's really going on there, though, with the normal force? I mean, what's causing, if we talk about, I mean, what's providing the normal force?
Action of the weight versus the reaction of the
So it's got to be something about, it's got to be the forces within the table, right, that maintain the structure of the table, right? When you set something down on the table, you may not see it, but it's going to buckle very slightly. It has to. It has to, because what it really is, it's an elastic response to the weight of the dog food sits on the table. And in order to generate that force, that return force, something has to be elastically deformed a little bit in the table. It might be very, very small, but it happens, right? It happens. It happens on a molecular level. These molecules get pulled apart slightly. And really what it is, it's the electromagnetic force that we'll talk about later, is what causes that elastic deformation. And the further the objects get apart, the stronger the molecules get apart, the stronger the elastic force, return force is that offsets the weight of the bag, right? And we'll get into that stuff more in the future. But that's really what's causing it. But for all intents and purposes here, for us, we can assume that the table is rigid, which for, I mean, you know, how do you define rigid? You know, at some level, nothing is rigid, but on an everyday level, it stays pretty rigid, right? And it's bearing the force with that contact force. Okay, so let's look at another example then. Let's go to the next level here. Let's look at something like this guy. Okay, so these rocket sleds. Prior to manned space flights, we did a lot of testing on the ground with these rocket sleds. People did crazy stuff when we were trying to go into space. Oh gosh. If you ever get a chance, listen to some stories about some stuff that Chuck Yeager did. Chuck Yeager did some just crazy stuff, like when they were testing the X-15 and all these bizarre, X-15 was essentially just a rocket strapped with a couple little tiny wings, and they dropped it off the belly of a B-52. And it just, they didn't know what was going to happen. It didn't ignite for a while, and when it did, it just took off. It almost went out of the atmosphere. It almost wouldn't stay in the atmosphere. It was skipping off the edge of the atmosphere when it started to get more dense, and he just about didn't make it. The thing just about went off into space, and he would have died. Those guys were nuts. They were absolutely nuts. I mean, they just, yeah.
Didn't he like almost pass out?
Yeah, I mean, he would have died. He would have gotten,
Well, like,
But
like
like,
all the way up
while
there,
he
didn't
was
he
doing
almost
it.
pass out? Before
Yeah,
he could come
the
back
G-forces.
yeah, the G-forces were
down? In the
huge.
black box.
Yeah, it was, and then they didn't think they were gonna be able to land the thing, you know, because it was just like, it had almost no aerodynamics at all. I mean, it was just like flying a piece of metal. It was, yeah, they were crazy. So anyway, what about this? Here's an example of some numbers that are sort of based on what they did. So they've got this rocket sled, and it's mounted on some rails, and it's like a little train car going down this rail. So the initial acceleration is about 49 meters per second squared, high or low? Is that pretty high or pretty
That's
low?
really high.
That's pretty
Yeah,
high.
it's like 5 times the gravity.
Yeah, that's a little bit more than, well, it's about 5, it's actually a little bit less probably, but it's really close
Almost 5
to,
Gs, that's-
really close to 5 Gs. 5 Gs is a lot. 5 Gs is a lot. So how much, if you weighed 200 pounds under 5 Gs, what would your weight feel like? 1,000 pounds, yeah. So that's a lot. I mean, it takes a pretty strong person to squat 300 pounds, right? And so, I mean, that's a lot of weight. So really high acceleration. The mass of the entire system is 2,100 kilograms. And we know that the force of friction that was opposing the sled was about 650 newtons. Okay? So how are we going to come up with what do we want to find here? We're trying to find the force, what's it asking for? Magnitude of the force exerted by each rocket. Okay? We want to find the thrust exerted by each rocket. So what can we do? This kind of gets us started on the idea of solving a dynamics problem. What do you think? So here's a nice colorful picture of what's going on. That represents things okay, doesn't it? I mean, what are these? There's 4 engines. What does this mean?
There's 4 different thrusting forces.
Okay, so what must T represent here? What do you think T represents? Thrust of each engine. Okay, that looks good. What about this stuff right here?
Force and weight.
Okay, the weight of the object, and then the normal force is being provided by what? Say it again.
The rail.
Tracks. Yeah. Is that really crucial here?
No.
Not so much, because they must cancel out. How do you know they must cancel out?
Because it doesn't fly away or anything.
Yeah, it doesn't accelerate up or down. It just moves horizontally along the rail. If they didn't cancel out, there would have to be some net acceleration vertically, right? And we don't see that. And then, what's this little f?
Friction.
Friction. Okay, so that's, and then it results in, I guess, some acceleration up here, right, that we know. Okay, that's not bad. That tells a pretty good story, but in physics, that's a little too flamboyant. What do we want to do instead?
Free body.
Right, free body diagram. And what are our rules for a free body diagram? It's been a few days since we talked about this. So we make a point that represents the object. So there's the sled, okay? And then what do we do with all the vectors?
They add tip to tail pointing away from you.
Could they emanate from that point then? Yes, ma'am.
Why is it called a free body diagram?
I don't know.
There's some
I
scientists.
don't know. I've just called it
I
that
mean,
my
is it-
whole professional life.
The body, prior to adding in vectors, is free of any force. I think
That's probably it. Probably something along those lines.
it's just a point without,
And then you're just going to add the forces to the point. It's probably something very much like that. But that's what we call it, is a free body diagram. And does it make sense that this would be the appropriate free body diagram?
Yeah.
Right, because looks like we've got 4 forces all adding tip to tail to the right. We've got one little force acting to the left, and normal force acting up, weight acting down, and they cancel out, okay? So now what we want to do here, though, is if we're going to try to figure out what these, all right, so if we want to be able to solve for one of these quantities, thrust, we've got to turn this into an equation or a set of equations. And so we've got to kind of think backwards here. Like, what if we were taking even a different kind of problem that was maybe even a little more difficult where we were doing something, what if I've got one queued up here, I can't remember. Like say something like this guy, that's kind of the next thing we're gonna tackle. If we wanna know, for example, what the acceleration is of this guy, right? We're trying to solve for A, and we'll get there in a sec. Let's kind of reverse engineer how we're gonna get there from our free body diagram, right? We know that our net force by Newton's second law equals what? What is Newton's second law? F equals
MA.
MA, good. Right? And that's net force. When we say, Newton's second law really means net force. So if we could just come up with the resultant force, it'd be easy for us to always correlate that with acceleration, wouldn't it? The two just go hand in hand. It's a minor step to go from net force to acceleration or vice versa. Right? That's not a big deal. It's getting here is what we want to do. So how are we going to come up with the net force? Now, it's a vector quantity. You've had some experience with vectors. How did we build resultant vectors? Because that's all this is. A net force is just the resultant force vector, right?
Yeah.
How did we build those in the past, resultant vectors? Okay, we added them tip to tail, but if they weren't nice orthogonal vectors that were all at right angles, we had to do something else. We used some trig, right? And what did we do with the trig? We made a table, right? And the table consisted of two columns, right? The column, we had an X component column and a Y component column. And then we just added up, right? We added up all the, the X component was what we had in the past, the horizontal components of all the forces, or they weren't forces at that time. I think they were just probably displacements or something, right? And then we added up the Y components of all the displacements. And then we ended up getting a net X displacement and Y displacement, right? And we added those up tip to tail. Finally, once we got the resultants, the components, sorry, the X and Y components, we added those in one simple right triangle to get the final resultant displacement. Okay, we're gonna do the same kind of thing here, right? That's our goal. We want to be able to build this, build some orthogonal components that we can put together to come up with the net force. And maybe we don't even have to come up with the net force. A lot of times we may just want to know a part of one of these equations. So we call these equations that contribute to the net force, really flashy name, we call these the equations of motion. And all they really say is, we could kind of reverse engineer this. We're going to take we're kind of working backwards because we're given in this case, or this represents the resultant vector, right? That's where we're trying to end up. So if we work backwards, this comes from the components of the net force, right? Just like before, the resultant came from r sub x and r sub y, right? So we want to come up with equations that represent the x and y components of that. Well, don't those just come naturally from the free body diagram? Because we've got this broken up, in this case, into the horizontal forces and the vertical forces, right? So we could break this down and we could say this came from the x component of the net force, which is what in our free body diagram? Now we're assuming here that this is the positive x direction, and that's the positive y direction, right? So if we adopt those conventions, what equation do we get out of this thing? What is our net force equal to?
4t minus F.
Everybody see that? 4t minus friction, right? Because I get 1, 2, 3, 4 t's pointing in that direction, minus little f. And what is that equal to? What is the net force in the x direction equal to? But what's it going to be in terms of Newton's second law?
Equals
Ma sub x, yeah. Right? Because Force goes with acceleration. Force causes acceleration, right? So the direction of force must equal the direction of acceleration. So if there's an x component of force, that's what's contributing to the x component of the resulting acceleration, isn't it? So here is equation number 1, right? Equation number 2 in this case is kind of superfluous, right? What is the net force in the y direction? We assume up is positive, so n minus w, so mg, call it mg. And what's that equal? 0. So what's that tell us? It does tell us something significant, but it's not crucial to this problem. If I solve for n, what's it tell me? N equals mg, right? Okay, now, but even though that's not telling us much, isn't it cool how the equations dictate exactly what's going on here? I mean, they shouldn't say they dictate, they parallel exactly the physical situation. When you solve for n, it equals weight, which is exactly what we'd say. The normal force is offsetting the weight, right? Okay. All right, so then all we'd have to do, if I want to solve for t in this equation, because that's what we're trying to find, is what? Algebraically, how do I isolate t?
Plus,
Add f and divide by 4. Okay, good. So we'd end up with thrust equals m a sub x plus friction divided by 4. And those are all things we know, aren't they?
Yeah.
Right? We know the mass, they gave it to us, it was 2,100 kilograms. We know the acceleration, right? A sub x is the only acceleration, isn't it? That's the total acceleration. That was 49. And they even gave us the frictional force was 650, right? So we can easily solve for t there, right? Okay. We won't do it, but we could. It's gonna be a big number, yeah, and it should be. I mean, rockets produce a lot of thrust. Okay, what about this one? Let's look at this skier. I like this one. This would be a great place. If we get through this today, this would be good. Consider the skier on the slope. Okay, her mass, including equipment, is 60 kilograms. What is her acceleration if friction is negligible? And what is her acceleration if friction is known to be 45 newtons? Okay, so let's do the first one first, part A first. So what are the forces acting on the skier then? Normal force. Okay, in what direction does the normal force act?
Perpendicular.
Perpendicular. Okay, and here's where, I don't know if we get this far today or not, but normal means perpendicular. That's literally the meaning. It's our more mathy word for perpendicular. We wouldn't talk in calculus about perpendicular. We talk about a normal line, right? Remember us talking about that already? The normal line is the one that's perpendicular to the tangent line. Okay, so normal is normal. The normal force is normal to the surface always. And later on, when things get more complicated in college calculus, we're talking about calculus of multiple variables, and so you're not talking about just a function, you're talking about maybe a surface. Well, then the normal vector to the surface might be pointing, it's going to be pointing, it might have other components other than just x and y components. It's going to maybe be pointing out of the board a little bit or something too, right? So we got normal force pushing up. What else? Weight pushing down. And is there any, if there's no friction, is there anything else going on?
No.
If there's no friction, that would be it, right? If there is friction, then we'd have to include a little backwards vector that's always, and in what direction is friction? We'll talk more about friction in detail in the near future. But for now, yeah, it's resisting motion, isn't it? Right? So it's always pointing opposite direction of motion here, okay? Okay, so then this is a pretty good picture, but way too flamboyant for physics, right? We want to make this simpler. We don't need all the bells and whistles there. This is a 25-degree angle. Okay, so now if we look at these vectors, what would be the natural choice for our orthogonal coordinate system? Because we want to pick a coordinate system. The directions we pick have to be at right angles, but we'd like them to match the problem as well as possible. So in this case, x and y really doesn't work so well, does it? Now, part of that is we want the orthogonal coordinate system to match the directions of as many vectors as possible to make, so we don't have to break so many into components. We only have 2 in this case, and so you might argue, well, the weight's acting vertically and the normal force is not, so it's 50-50. Why not just choose X, Y? Why would that still be a bad choice?
Friction.
Because you don't know the angle of the normal.
Well, we do. If that's 25, we can determine that, right? But and if there's, we'll assume there's no friction here. But even if there's no friction, our equations of motion are going to be they're not going to work as well. If we choose X and Y, what's the problem? There's a big disadvantage to that.
The acceleration isn't going to be, and you're going to have it in 2 parts.
The acceleration is, there's going to be an X and a Y component of acceleration. That's cumbersome, right? We'd rather not do that. If we choose this kind of a reference frame where that means parallel and that's the symbol for perpendicular, then the acceleration is all going to be in the parallel or anti-parallel direction, right? Does that make sense? In this case, the negative parallel direction. I would have defined it as down instead of up. You're free to do it however you want it, right? We could instead, everybody see that? We don't have to do this. We could make it go in that direction if we want to. As long as we're consistent, it's fine. But let's just do what they did, I guess.
Change the textbook.
Right? But that way the acceleration's all parallel, and so we can solve for acceleration in just one of our equations of motion. It doesn't have to show up in both. Big advantage. And just think of it conceptually as this way the orthogonal directions, one of them matches the direction of motion, which just inherently seems like a good idea, right? So then here's our free body diagram, right? Let's go ahead and include the friction in there too. And then we can take it out later if we want to look for part A. So here's our free body diagram. Okay, what can we do with that free body diagram though? That doesn't look as easy as this one did, right? Here it was pretty straightforward. We saw that all of the horizontally acting forces were just right there. All of the vertically acting forces were right there. What's different about this one? Well, 2 of them work great, but yeah, this one's a little bit off, isn't it? It's not acting in the parallel or perpendicular direction. So what do we have to do to that one?
Turn it into a parallel.
We've got to break it into components that are in the coordinate directions, right? For our reference frame. So this is the book doesn't use this word, but I want to throw this one at you. This is a free body diagram, but this is, if we make that trade, the weight for these 2 components, that's an orthogonalized free body diagram. This is the holy grail. This is what we want to get to. Because now, all of the forces, it becomes as easy as this last problem was, right? Where all we got to do is add them up in one direction. Some are positive, some are negative. Other coordinate direction, some are positive, some are negative, right? So if we can get this to look like this one up here, then it's simple. The equations of motion just follow the forces acting in one direction and the forces acting in the other direction, right? Well, that's not a big deal. We got to think about a little bit of geometry here. Does everybody agree, and let's just talk a little geometry for a second. If this is a 25-degree angle, then what if I extend that vertical vector down and make a right triangle out of it, right? We want to know what is this angle right here, okay? That's a right angle. If that's 25, what's that one?
95.
So 65, right? Okay, well, would you agree that this vector, this component, and that component are also at a right angle? So what's theta? 25, right? See what I'm saying? So, because a lot of times there's a question, does the theta go, if that's theta, does theta go there or does it go there, right?
Will it always be that angle?
It will, yeah, for this reason, right? Here's a little hint, this is a little trick that I use all the time in physics. principle of exaggeration. If you're not sure, because maybe it's a slightly different situation than this, exaggerate the triangle so the two angles look vastly different, right? See what I'm saying? If this is, like, what if the angle is really 44 degrees? Well, it's tough to tell if it's 44 degrees, but make it much smaller than that. So if that's theta, and this is, that's your vector, well, it's pretty obvious when I break that into components, tip-to-tail components, that that's the small angle up there, isn't it? So that one's got to be theta. See what I'm saying? So the principle of exaggeration oftentimes will just reveal, you know the relationship exists, but which angle is it? Exaggerate the triangle and you'll see. Okay, so then if we do this, this is the angle theta, which is, I'm going to call it theta, so I have to write 25 the whole time, but it's theta is 25. Then what's going to be, in terms of SOHCAHTOA, what's the parallel component of the weight going to be? Yeah, going to be the weight times the sine, because it's an opposite side, right, of the triangle. So we're going to get parallel component is W sine theta. The perpendicular component is going to be W cosine theta. And W is just mg. We can make that substitution also. And so then we end up with this picture. So let's get rid of this, because this is really a little bit confusing in a way because it's got both the components and the vector drawn. We'd really like to get rid of, I'll do this. I'll do this, how about? We'd really like to kind of, whoops, our color. We'd like to do this. Right, we're going to split that into those. That's what we did. Right, so now if we draw all these vectors, what are they? Here's our object in the center. There's our body. We've got the parallel component of weight. So that's just mg sine theta. Right? We've got the perpendicular component of weight, mg cosine theta, and then we've got the normal force right there. Okay. Would I ever put a negative sign on any of these? You're right, I wouldn't. How come?
Because that would just mean it's pointing in the other direction.
Yeah, the direction tells us the sign, doesn't it? So now let's write our equations of motion from this. So this is the parallel, that's the perpendicular. So the first equation of motion we could write like something like this. The net force in the parallel direction, so the parallel component of net force, is what? And let's go ahead, I know we called this the positive direction, but why? Why don't we call this the positive direction instead? Let's go ahead and do that, right? So we don't have to mess with an extra negative in there. So what is the net parallel component of force?
mg sine theta.
That's it. Oh, and then if there was a friction, yeah, let's add the friction also. So if there was a frictional force, it was acting in that direction, right? So down here it'd be the same thing. There's our frictional
It would
force.
just be
Right.
mg sine theta minus f.
Okay, so we're going to get mg sine theta minus f, and what's that equal to? Say it again? MA, yeah. And technically it's A parallel, but that is A, because all the acceleration is parallel, right? Okay, so there's one equation of motion. What's the other one?
The perpendicular.
How about in the perpendicular direction?
And is mg cosine theta.
Equals,
Acceleration perpendicular.
yeah, but what is the
Or zero.
acceleration? It's zero, right? There is no acceleration off the slope.
Can that ever not be zero?
Well, I mean, it could be, but we almost always want to choose it so it is zero. There will be some times when it won't be, yeah. But whenever we can, we prefer to avoid that. And so then if we were trying to find acceleration, is that what we're trying to find? So if we want to solve for A, what would we do here? What's the one step? Here's my equation, right? What do I have to do to solve for A? What do I do?
It's mg sine theta minus f.
Y by m, yeah.
Yeah.
So I'm gonna get A equals mg sine theta minus friction over m. So if I want to write that as, let me separate that. So if I want to split terms, I just get g sine theta minus friction over m, right? G sine theta, and do you see that? That's kind of cool, right? What did this do? I mean, that gives you, even, I want you to get in the habit of doing that. That's what really makes physics cool, is when you start to look at this and say, okay, that's telling me something kind of intuitive about the way the universe works. The m's cancel, but I'm multiplying g by sine theta. Well, that's almost like you're just diluting gravity a little bit, aren't you? Because it's not going directly down, it's going down an incline. So we're diluting it by that factor, right? Doesn't that kind of make conceptual sense when you think of it that way? And then this other term over here, well, I mean, that makes sense too if you want to. Friction is the force that's acting, and the friction by itself may not mean much, but when you divide it by the mass, it tells us what impact that frictional force really has, right? We can plug in numbers now. So if sine theta, let's do this, pull the calculator and actually get an answer. Are we out of here like in a minute?
Yeah.
Oh. All right. Well, we could put numbers in. We won't, but we don't have time.
Could. You could.